Okay, so how's everybody doing? This is the first time I've seen you guys since you submitted your games. How did that go? Yeah. Were you happy with the games that you made? Some of you, yeah. Good. So we got about 215 submissions, and it's hard for me to tell who's dropped the course and who's not. So could be that there's it could be that there's 300 people registered in this course, or it could be that there's only 250 left. I can't tell because the system doesn't take you out when you drop, and also you're not obliged to drop even if you intend to drop until the last day of classes. So I'm hoping that most of you submitted something for this last assignment. Okay, so last class we were looking at algorithms, and we'd seen a few sort of different tricks and things. We looked at sorting algorithms, we did binary search, and some sort of tricks there. And we got this, we had made this table which showed us comparatively different functions of n and their values depending on n, and so we saw, there's this function log of n, which is roughly how many times you can divide n by 2 before it becomes smaller than or equal to 1. It's a very slow growing function, so even when n is, let's say, 1 billion, log of n is still only 30. N log n was a little bit faster growing, so it's n times log of n. So it grows a little bit faster than n, but not a ton. And then n squared is this really very fast growing function as a function of n. When n is 100,000, I think we decided that would be something like 10 billion or something. So, so we have this ordering on these functions, and why do we want this? Well, it's because these functions often describe running times of algorithms, and we like to know which ones are faster. So here's the ordering. O of log n is really fast. It's much faster than n, so this is the binary search running time. Much faster than n, which is like the time to scan a whole array, which is faster still than n log n, though not by quite as much, not quite a difference. And then we have n squared, and we can go up to bigger powers of n cubed, n to the 4, n to the 5. Whoa. Hopefully this roof doesn't come falling in on us. Yeah. Yeah, that's exciting. So, and then there's 2 to the power of n. So what I've shown you is basically a grab bag of things, and now what I want to talk about is, well, when you're given a problem, how do you go about solving it? Unfortunately, there's no good answer for that. So most of what I do research-wise is finding problems or having people ask me problems, and then I try and come up with algorithms for them. So there's no recipe for finding the best algorithm for a problem. It involves a lot of experience and a lot of practice, basically. And the experience part is basically, as you develop as a computer scientist, you'll learn more and more techniques for solving problems. And when you're presented with a problem, you basically run through your checklist of techniques that you know and say, well, can I use this technique to solve the problem? Can I use this technique to solve the problem? Can I use this technique to solve the problem? Many times there'll be more than one technique that solves the problem, but some may run faster than others, so you would like to solve it the fastest way possible. So here's a list of problem-solving techniques that we've learned so far in this course. and we'll look at some examples of problems that can be solved with them. So, can the problem be solved with a variant of binary search? So really, these kinds of problems are after looking at a bit of the problem, we can cut it in half. Okay. That's basically what binary search does. It looks at the middle, and based on whatever it finds there, it cuts the problem in half, either the first half or the second half, or maybe even it's done at that point. So what kind of problems can be solved this way? Well, here's one. The problem is find the value x in some sorted array A. That's easy to do. That's exactly what binary search was made for. We had a sorted array A. We wanted to find the value of x. How do we do that? Well, we look at the middle element of A, and if x is smaller than that value, we recurse on the first half of A. If x is bigger than that value, we recurse on the second half of A. And if x equals that value, then we've found it and we're done. Okay. So that is the classic binary search problem. Here's one from the tutorial this week. Suppose I give you a sorted array, and in the tutorial it specifies that the array contains only zeros and ones, which really means it's just a sequence of zeros followed by a sequence of ones. And I ask you to find the first one in that sorted array. So how would you do that using something like binary search? Let's see what that looks like. So I give you a sorted array, it has a whole bunch of zeros, followed by a whole bunch of ones. And actually, it doesn't matter if it's only zeros and ones. The technique that we'll look at is we'll actually solve it for any sorted array. So the thing that I'm looking for, the thing that the problem is asking me to find, is the location of this first one. So, well, the standard binary search paradigm says what we should do is look at the middle and decide what we need to do based on what we see there at the middle. So we look at the middle, we see that there's a value 1 stored there. So what can you deduce about the location of the first one based on that? So if you, yep. Okay, so it could either be the value we're looking at, because we're looking for a 1, we're interested in the first one, or it could be to the left of it. But it's definitely not any of these values. Okay. So it's definitely not any of that stuff. So just by looking at that first one, we can discard that second half of the array. All right, and then we recurse on this little part of the array that's left. So maybe the next step is to look here. And there we see a 0. So what can we deduce from that? It's to the right, or more specifically, it's not the element we're looking at, because we're looking for a 1, this is a 0, and it's not anything to the left of that because they're all smaller than, they're all less than or equal to the one we're looking at, and so it must be whatever's left after we cut that out. Okay. So basically we have that if a at I equals 0, then we discard A0 up to AI, and if A at I equals 1, then we discard AI plus 1 up to the length of A minus 1. So we'll be calling the length of A, we'll be calling that n. So in either case, whether we see a 0 or a 1, we get to discard half of the array this way. Okay. And then this process finishes when we get down to a single element or no elements. If there's no elements, then we say, hey, there's no 1s in this array. And if we get down to a single element, we just need to check if it's a 1 or a 0, and that'll give us the answer. Okay. So that's a problem that, it's not exactly searching for an element in a sorted array. It's searching for the first element in a sorted array, but it can still be solved using binary search. So that's one of those binary search type problems. Here's another one from the tutorial this week, and it's a little bit trickier. So here you have a sorted array, A, that's supposed to contain distinct integers. So no integer occurs more than once. And we want to know if it has what's called a fixed point. And a fixed point is a location I where the value stored at that location is actually I. So if you think of the array as a function which maps indices onto the value that's stored at the array there, in mathematics that's called a fixed point. A function that maps x onto x is what's called a fixed point of that function. And so we'd like to know if this thing has a fixed point. So this is certainly an easy condition to check if A at I equals I. So there's certainly an easy algorithm which just goes through the array looking at one element at a time and deciding if it's, the algorithm is, for I in range length of A, if A at I equals I, return true, otherwise return false. The fancier version of this is to realize that actually we know enough about this problem that we can use binary search. And that's not immediately obvious until we think about it for a little while. So let's draw a graphical representation of a few different things. So we'll draw two axes. We'll call this one the I-axis. And this one, I don't care what we call it. Let's call it Y. And here we will, so down here is 0, 0. And what we'll draw is just the line y equals I. And not everything on that line, but just the integer points. Okay. So this is the line y equals I. Nothing fancy there, right? You just set the y coordinate equal to I, you set the I coordinate equal to I, and you get these points, and you do that for all these integers, 0 up to, let's say, n minus 1. All right. Now, let's look at the values that are stored in the array A. So we'll draw another thing in red, which is y is equal to A at I. So for example, maybe A starts with a minus 3 and some more values. So in that case, well, this says A at 0. So over here on the 0 for the y-axis, we want that to show up as a minus 3. So that's down here. Do that in black. minus 3. So that's how that thing gets represented, is it's that point over with I coordinate 0 and y coordinate minus 3. Now, what can you tell me about A at 1? So the things I know about A are that it's a sorted list, it contains only integers, and all the integers are different. So what can you tell me about it? Could it be minus 5? Yeah. It's going to be a bigger number than minus 3. And it only stores integers, so it's actually going to be bigger than or equal to minus 2. Right? There's no two, all the elements are distinct, so it can't be minus 3. So it's got to be bigger than minus 3, and the next thing is minus 2. So the next element here, doesn't matter what it is going to be bigger than or equal to minus 2. So I don't know. Let's just play with it and see. Let's say that it's minus 1. So then that puts it right there. That's minus 1. Okay. Fine. And the element that comes after that, well, using the same reasoning, that thing's bigger than or equal to 0. And let's say maybe it is 0. So that puts it there on the giving a y coordinate of 0. And then the next one has to be bigger than or equal to 1. So it can kind of track this line y equals I. So it kind of has to at least keep up with y equals I. It's increasing by at least 1, but sometimes it increases by more than 1. So let's say this was 1, and let's say 2, 1. Let's say the next one is 4. So 4 there. 1, 2, 3, 4. That would put it right there. So actually, this would be a solution to our to the problem that we're trying to solve, right? Because this is array position 0, 1, 2, 3, 4, and the value that's stored at the array right there is 4. And then after that, what do we know about the next element? Well, it's bigger than or equal to 5. So it's either on this line here, this line y equals I, or it's above it. If it's equal to 5, then it's also on this line, or if it's above it, it's above this line. Okay, so I don't know. Let's just say that it is 5. So that would put that point there. And then the next one would have to be bigger than or equal to 6. And let's pretend that it's actually bigger than, so maybe it's up here. That would give it a 7. And now after that, everything else in the array is going to be above this line y equals I. Okay? Because everything else has to be at least 1 bigger than the previous one. We're already above this blue line y equals I, and we're going to stay above it because we can't get back down. We're going to grow at least as fast as this blue line. So the two things separate and never touch each other again. Okay. So if we connect the dots here, we get a picture like this. This is sort of like the function a at I, and this is the function I. So it was looks like that. And what's the thing that we're looking for? Well, we're happy if we find either this thing or this thing, because these are two locations, 4 and 5, where the value stored in A is actually equal to the index of that thing. Okay, so now let's say I start doing binary search. So I'll use this binary search idea, and I'll look at A at the middle location, and suppose that thing is bigger than M. So this is one of these locations where A at I is bigger than I. So in this picture here that shows y equals A at I versus y equals I, where is that thing in this picture? So is it on the right side or is it on the left side? Here's the middle. This is the left side of the picture. This is the right side of the picture. So if A at M is bigger than M, that means M is somewhere over here in this picture, right? Because this is A at M, this is M. So that means we're over here on the right side of the picture. And then what can we deduce about this value that we're looking for, this fixed point that we're looking for? Where won't we find it? Yeah, we won't find it anywhere after this location. We can scrap off, throw out this part of the array, right? So this is M, this is A at M, and we know we're not going to find it over here at all. On the other hand, if I have A at M is less than M, that means I'm over here on the left side of the picture. That's a picture that looks like this. Here is, this is M. This is M. And this is A at M. So that has A at M less than M, which means the thing that I'm looking for is not over here. Okay. So that is actually this value here, this 1, which is stored at position 3 in the array. And that tells us the answer we're looking for is not anywhere over here. So if A at M is less than M, we know we can throw away everything up to the point we're looking at. If A at M is bigger than M, we can throw away everything after the point, including the point we're looking at, and everything after it. And if A at M equals M, well, then we're done. Then we found a fixed point. That's one of these guys here. And we can just return the value M and say this is the fixed point in the array. So this is another problem where you can apply binary search, because just by looking at one value in the array, you can determine whether the thing you're looking for is this value you're looking at, or whether it comes before, or whether it comes after. So all of these things can be done with binary search, which is great. So after looking at a bit of the problem, we can cut it in half. More specifically, by inspecting A at M, we can discard at least one of A at M plus 1 up to the end of the array. Well, let's write it. Let's use the Python notation, or A up to position M. And we want to be able to do that in constant time. So if we can do that in constant time, then each step we do discards half the array, and we'll only have to do log n steps, so that'll give us a log n time algorithm. So that's great. So any questions about that application of binary search. So the basic, the basic thing is, if you can get rid of half the array in constant time, you're good. Now the problem with binary search is it really requires very specific kind of inputs. So the array has to be sorted, for instance, for the applications that we've looked at, or all of the zeros have to come before all of the ones, which is actually another way of saying that the zeros and ones at least are sorted. And there's not a ton of cases where you can assume that the input comes in that way, which is too bad, because otherwise we could solve a lot of problems really, really fast. On the other hand, it's sort of expected, because this thing solves a problem without even looking at all of the data. So it solves a problem of size 1 million only looking at 30 elements. There's certainly going to be a lot of problems where we have to look at least at all the data. So your next question, if there doesn't seem any hope of using binary search, can you solve it with a for loop? So is there just an easy algorithm that just scans through the input to look for the solution? So what are examples of that? Well, each of these three is an example of that also. Okay. If I'm looking for the value x in the sorted array A, well, that's really easy to do. I just go through the array and see until I find the value x, or I don't. So for example, find the location of x in the not necessarily sorted array. Well, there's lots of easy ways to do that. For example, I can say for I in range length of A, if A at I equals x, return I. Otherwise, we'll return something that means it's not there. So this will find the location of x in some array A, or it'll return -1 if x is not in A. So that's pretty clear that this running time for this code is O of n. Right? This is a loop that iterates n times. This is a test that takes constant time but executes n times. And this is something that takes constant time. So in total, the thing that dominates is the n executions of this line right here, which means it's going to take order n time. We're inspecting every element in the array. Another category of problems like this are these summarizing things where you want to take the array and turn it all into one thing. So for example, here if we want to compute the product of all the elements in A, so A0 times A1 times A2 times A3, all the way up to A dot length of A minus 1. How do we do that? There's a couple of different ways. What's the sort of most straightforward way, the way that you would think of if you had never learned much about Python but knew some other language? For loop. So you do something like keep a counter, which is going to keep track of this product, and say for x in A, C equals C times x. Right? You start with this C equal to 1, and then you multiply it by A0, then you multiply it by A1, then you multiply it by A2. At the end, this thing is the product of A0 through AN minus 1. And again, this is just a simple for loop. It executes n times, and the statement that you execute in there takes constant time. So this is going to take O of n time. How about factorial? Is that one we can do with a for loop? Yeah. So we can do this for, let's say, I in the range 1 up to n plus 1, c equals c times I, return c. So that'll compute n factorial, or since we've already written a product function, we could also do return the product of the range 1 n plus 1. That's another way to do it. So this long-winded way, you look at the code, you can see that it runs in O of n time because of this loop that executes n times. If you do it the shorter way, you have to go and look at the code for product to see how long it takes, but that also takes order n time, so all of the complexity is hidden in there. Okay, so now it's time for you to start paying attention because there's something relevant to the assignment here. Anybody heard of the Fibonacci numbers? Yeah. So anybody know the story of what Fibonacci numbers are supposed to model? Yeah.
Rabbits.
Yeah. So they're supposed to model the number of rabbits that you have if you start with 2 rabbits of different genders and leave them alone for some number of generations. Then after n generations, you should have the nth Fibonacci number of rabbits. So you start out with the 2, and then those 2 mate, and they make 2 children, and then those 2 children mate with one of the previous ones, and so on. And this is supposed to somehow represent how many rabbits you'll get after n generations. So I don't know if this is a reasonable model for rabbit behavior, but in any case, it turns out these Fibonacci numbers are important for a lot of other things. It's probably not a good model for rabbit behavior, but they're important for a lot of other things. So the definition is Fibonacci of n is equal to 1 if n is 0 or 1, and otherwise Fibonacci of n is equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2. That's the definition. And actually the definition immediately gives you the code for it. So you say if n is less than or equal to 1, return 1. Otherwise you return Fibonacci of n minus 1 plus Fibonacci of n minus 2. So that's the code for computing Fibonacci numbers. Let's test it out. So fib of 1 returns 1, fib of 0 returns 1, fib of 2 is fib of 1 plus fib of 0 is 2. What's fib of 3? So it's fib of 2 plus fib of 1, so it's 2 plus 1 is 3. What's fib of 4? 5. And how about fib of 6? 8. And just so we all get it, how about fib of 7? 18. 18? Oh, yeah, fib of... okay, let's do this carefully. 1, 2, 3, 4, 5, 6, and fib of 7, 8 and 13 is 21, and fib of 8, 21 and 13, 34. Okay. And fib of 30 is up around 1.3 million. Okay. And fib of 100, well, we don't know what that is. Seems to be taking a long time to compute. Um, so that's interesting. So this seems to be a slow algorithm, right? This thing that we've just implemented must be slow, because even for n equals 100, this is taking a really long time. And everything else we've seen, for n equals 100, that was nothing. That was no problem at all. So let's think about this for a bit. So it turns out that fib of 100 is some number, and we'll see it shortly. I think it has about 20 digits. So want to tell me what fib of 9 is? 55. So you guys did that really quickly. And I'm certain you didn't count to 55, one step at a, 1, 2, 3, 4, 5, all the way up to 55, which is essentially what this algorithm here has to do that. It has to make a big recursion tree with 55 leaves that it adds up, each one adds 1 to the sum. So how did you do it? Yeah. I told you the values of fib at 7 and fib at 8, and from that you knew the value of fib at 9. So this suggests that there's a faster way to do fib. And while we can still use this if n is less than or equal to 1, return 1. Otherwise, we can just compute all of the Fibonacci numbers, fib of 1, fib of 2, fib of 3, fib of 4, and so on, even fib of 0, and until we get to fib of n, and then that's the value we want to return. So we'll use an array for that. So we create an array. Initially it contains all 1s, and it'll contain n minus 1 of those. So what I know now is that a at 0 equals 1, which happens to be the 0th Fibonacci number. And I also know that a at 1 equals 1, which happens to be the first Fibonacci number. So in general, what I want is that a at I is equal to the ith Fibonacci number. So I've already got that for a at 0 and a at 1. Now I just need to get it done for 2 up to n. So how do I do that? Yep. Okay, so go through the array starting at position 2. That'll keep us away from 0 and 1. And we'll go all the way up to n. So in the range, that means the second argument is n plus 1. And if we do things in this order, then we can just say a at I is equal to a at I. Just apply the definition. Minus 1 plus a at I minus 2. Right? So if we already know the I minus 1th Fibonacci number and the I minus 2th Fibonacci number, then we know the ith Fibonacci number. It's given by that equation there. And we do this for I starting at 2. When we do it for I equals 2, well, we already know the two numbers we need, a0 and a1. And then we move on to I equals 3. Well, now we've just computed for I equals 2, so we know I equals 2 and 1. Then on to I equals 4. Now we know the answers for 3 and 2, and so on. And then eventually, what do we want to return from this thing? Yeah. We want to return the nth Fibonacci number. So we said fib of 30 was 1.3 million. How about this fib fast? So we index the list out of range. I minus 1, I minus 2. I didn't think so. Oh, here, this thing you mean. Yeah. The length of the array should be n plus 1. I don't know why I had minus 1. Okay, so fib of 30, 1.3 million. Fib fast of 30, 1.3 million. And somehow a little bit faster. How much faster? Fib fast of 100. It's really fast. No time at all. There's that 20-digit number that I was talking about. It was going to take us a while to get that by computing, by counting to that value, which is basically what the other thing was trying to do. And so there you go. We took this thing whose running time was terrible. In fact, its running time was equal to the value of the nth Fibonacci number. So here, the running time is O of fib of n, and the nth Fibonacci number is huge. I mean, for n equals 100, it's a 20-digit number, so this is going to be incredibly slow. Whereas this function here, what's its running time? Yeah, it's just the value of n, right? This is just a loop that counts from 2 to n and adds a couple of numbers together. So this reduces the running time to O of n. Okay. Big difference. Okay, so there's another kind of problem that can be solved using a for loop, faster than, for example, just using the recursive definition. Okay. All right, so if it can't be solved just with a simple for loop like this, well, maybe some data structure can help. And the two data structures that we know of are sets and dictionaries. And these things are good because sets and dictionaries, we've decided that you can add or remove an element from one of these things in constant time, which means that if I give you n items, I can stuff them all into a set or stuff them all into a dictionary in O of n time. So I don't really lose anything in terms of the running time by creating one of these sets if I'm going to have a loop that loops through n things anyway, and maybe that'll help me do these things. And typically these problems are for sort of matching problems where for every input element, what we're interested in knowing is whether or not there's some other specific element value that matches this thing. So for every x that we're given, we want to know if we were also given some number f of x, or some value f of x. So one example, which maybe looks familiar, here's something called a function called zero pair, which is supposed to determine if there's a pair ai and aj, so that if I add them together, the value is 0. So have we seen this this problem before? No? We've never seen it before? What's that? No. Many of you have programmed this before. You've solved this before. Yeah. Yeah. So what does it mean if ai plus aj equals 0? Well, that's the same thing as saying that ai equals minus aj. So we want to know, is there a pair, x and y where x equals minus y, or ai and aj where ai equals minus aj. So that's something we can solve by making a set. That takes linear time of all the elements that we have. And then we go through A, and we say if minus x is in that set, then we'll return true. And otherwise, if we go through the whole list A, and we don't find anything where we also find the negation, we can safely return false. So there are not a pair of elements whose sum is 0. Okay. So there's a problem that without using a set seems quite a bit more complicated. And if you just used an array, for example, this wouldn't have as good a running time. But as soon as you put everything in a set, it just becomes one simple loop again. And the point is that this test here, checking if minus x is in a set, this thing takes constant time. But of course, it executes n times. And if we didn't make the set, if we just instead said if minus x is in A, then this O of 1 would become an O of n, because we'd be looking through the entire array looking for this thing, and it executes n times, so the running time would jump up to n squared. Okay. All right, so there's something that suddenly becomes easier if there's a set that stores your elements, and we're already headed for a running time that's at least O of n anyway, so it doesn't hurt us to make this this set. So creating this set takes O of n time as well. Okay. Here's another one. I want to know if every element in A is distinct, or are there two elements in A that are equal. So, or is there a pair AI and AJ with I not equal to J such that AI equals AJ. So either everything is distinct, or there is some pair AI and AJ such that AI equals AJ. So how do we solve that with a for loop and a set? Yeah.
Could you just create like another variable and set it to the set of that array, and then just see if they're the same length? If then if there's any duplicates, the set would eliminate them. If they're the same length, then there would not be.
Yep. So here's the super short version of this code. We ask if the length of the set A is equal to the length of A. So if those two things are true, so if the set A, which gets rid of all the duplicates, has the same length as A, then that means there were no duplicates. And so every element is distinct. So there's the super version of that code, super short version of that code. And this takes O of n time, because here we convert the entire set A into, or the entire list A into a set. The more long-winded version of that does something like this. We create an empty set, and we say for x in A, if x is in the set, we return false, and otherwise, we add x to the set. So this way it just scans through, keeping a set of all the elements that we've seen so far. And if we see an element x that's already in the set S, that means we've seen x before, we would return false, because we found two things that are the same. And otherwise, if we haven't seen it before, we add it to the set and keep going. If we get to the end, of this, we'll return true, because everything is distinct. Okay, so sometimes making a set helps too. If that doesn't work, then we can use the fact that we know how to sort now, and we have a good idea of how long sorting takes. So we saw that the merge sort algorithm takes O of n log n time. So if we're willing to be a little bit slower than O of n, we can try sorting the input and see if that makes things easier. And sorting the input almost always makes things easier. So for example, if we want to know if X is in some list, well, if the list was sorted, we could know the answer to that really quickly. Unfortunately, it takes longer to sort it than it would be to just look through the list, so it's not a helpful technique for that. But let's look at maybe a couple of problems where it, or at least one problem where it is helpful. Well, here's one. Suppose you didn't have a set available and you want to know if all the elements are distinct. So how could I do that with sorting? Instead of using a set, how could I do that by sorting? So I want to know, are there two elements in the set that are equal to each other? Yep. Yeah. So I could say A sorted of A is equal to what happens when you sort A, and then say for I in range length of sorted of A minus 1, if sorted of A at I equals sorted of A at I plus 1, return false, otherwise return true. So the thing that happens when we sort is if we have two elements that are equal, then in sorted order they're going to show up side by side. One's going to be at position I, the other one's going to be at position I plus 1. And so if there are any two elements that are equal in sorted order, they'll show up this way. And so all we have to do is scan through the array looking at consecutive elements. We had this problem that was worried about all possible pairs of elements, and now suddenly it only has to worry about elements that come one right after the other in the sorted order. Okay. So there's a version of distinct. It's not as fast as the one that uses sets because it has to sort. Sorting takes O of n log n time, but it's still pretty fast. Here's another one that almost by definition reduces to sorting, and that's finding the element of rank of a particular rank. So some special cases of this are, for example, finding the largest value in an array. If I sort the array, where's the largest value? It's the last value. So that would be finding the element of rank n minus 1. What about the smallest value? That's the element of rank 0. It's at position 0. And in general, the element of rank k is the element that has k items that are less than or equal to it. And there's a slightly more technical definition here that's careful to handle the case where there's elements that are equal. But just think of it as, the element of rank k is what you get if you sort and look at the kth item in sorted order, which means all you have to do is return sorted of A at k. So there's the code for finding the element of rank k in a list that's not necessarily sorted is you just sort it and take the kth element. Okay. So there's some things that can be helped by sorting, and a lot of problems sorting is helpful, and it's usually built into whatever programming language you're using. So feel free to use it. And finally, if you get to a stage where none of the tricks you know applies, well, maybe you should just think about, what if I just try all of the possible answers? So if you look at the questions we've been asking things like, find the value x if there's a value equal to x in the array A. Well, there all we had to do was look at each element in A and we'll know the answer. We've also seen things like determine if there are two values, positions I and j, where A at I equals A at j. And we found a fast way to do that, but if we weren't that clever, we could have just said, well, let's just try all the different values of I and j and see if we find two things that are equal. And so for some problems, that's really going to be the best we can do, either because we're only that smart, or maybe there is just no better way to do it. So let's try that for a toy problem. So is distinct, which again is supposed to tell us if all the elements in A are unique. There's no duplicate values. And so we should return false if there is an I and a j with I not equal to j such that AI equals AJ. So how could we just do this in the most brute force way possible, testing all possible values of I and j? Yep. Okay. Okay. So what we want to do is pick a value for I, and initially I will be 0, and then we're going to try j 1, 2, 3, 4, 5 all the way up to n minus 1. If we find a pair that matches, we're done. We can return. If we don't, then we'll try I equals 1 and j equals 2, 3, 4, 5, 6 all the way up to n and so on. So this says eventually we're going to try I equals 0, I equals 1, I equals 2, I equals 3, and so on. And now for j, we'll start at I plus 1. So right, if I, for example, is 3, then we're going to try j equals 4, 5, 6, so on, all the way up to the length of a minus 1. And we'll say if a at I equals a at j, return false, because we found two elements that are different, that are at different locations in the array, but they're equal. And otherwise, by the time we get to the end of these two loops, we've tried every single pair of elements. So we've tried every possible I and j that we could try. And so we can return true in that case. So what's the running time? N factorial? No. N squared. So let's work through it. So this takes constant time. But it executes more than once, so we'll have to figure out how often it executes. Now, this thing here iterates n times. So this actually goes from I all the way up to, from 0 up to length of n minus 1. Now, what about this thing? So this iterates n minus I times, and well, this is not more than n times. So if we just want an upper bound, then this outer loop executes n times, and this inner loop executes at most n times each time the outer loop executes. So this takes O of 1 time and executes O of n squared times. So the running time of this algorithm is at most n squared. And I say at most because here we sort of said, well, this executes n minus I times, but we'll just say that's no more than n. So we're just overestimating it. But actually, if you think about it for a bit, you realize that somehow, on average, this executes something like n over 2 times. So sometimes it executes only once, but when it executes only once, there's another time where it actually executes n times. And sometimes it executes only twice, but when that happens, there's another time when it executes n minus 2 times. And so basically, on average, it executes about n over 2 times. So you get n times n over 2, which is n squared over 2, so some constant times n squared. Okay, so this takes O of n squared time. This is a really bad algorithm. Don't do this. But the nice thing about this algorithm is that it can solve any problem that asks for a pair of elements. So you can write somehow a general function that takes an array and some function which returns true or false. You give it 2 arguments and it returns true or false. And it can tell you if there's any 2 elements in that array which make the function return true. So we call this a satisfying pair. So AI and AJ satisfy the function f if they make it return true. And here, we'll return true if there exists I and j with I less than j such that f of aij is true. And all we do is change this. If f of ij returns true, we return true. And if we get to the end of this function and nothing returned true, we say there is no I and j which can make this, where ai and aj make this function return true. So notice we know nothing about this function except that it takes 2 arguments and it returns true or false. So it's a very general strategy. What if I wanted to do the same thing, but now I have a function that takes 3 arguments? AI, AJ, and AK. Is that more difficult to do? What's that? Yeah, but it's no harder to code, really, right? So the code just looks like this. That's the only thing that happens to the code. And now you have 3 loops. Each one executes at most n times. And so this n squared here becomes n cubed. But it can find any triple that you're looking for. So we'll take one quick example of that, of looking for specific triples. And these things look for, let's say, what are called arithmetic progressions. So 3 of these things work if you can find AI, AJ, and AK, so that AI is less than AJ, which is less than AK, and the difference between AJ and AI is equal to the difference between AK and AJ. So that sounds more complicated than it is. It's more easy to understand it by an example. So if AI is 21, AJ is 26, and AK is 31, then what we're really looking at are 3 numbers, which are 21 plus 21, 21 plus 5, and 21 plus 5 plus 5. So these things satisfy this, right? The difference between these 2 is 5, and the difference between these 2 is also 5. So that's called an arithmetic progression of length 3. So I want to write code that can find these things. So what does that code look like? Yeah. Yeah. Yeah, so that AI, AJ, and the I, J, and K can be anywhere,
Yeah.
and not necessarily even in that order. So I could be bigger than J, and so on. But, I mean, we have a definition of what we're looking for. We want this property to hold, and we want this property to hold. So let's just try all the A's, J's, and K's and see if any of them work. Of course, the ones, the I's, J's, and K's they were interested in are indexes into A, so we just need to iterate over those. And now, so now we're actually going to try every single triple, I, J, and K. And now we just ask, does this particular triple, I, J, and K work? Well, we need that AI is less than AJ, and AJ is less than AK, and AJ minus AI is equal to AK minus AJ. If all that is true, then we found our triple, and we can even return the triple I, J, and K. Otherwise, we get to the end of this thing, we've tried every possible combination that there is, we'll just return nothing and say it doesn't exist. So essentially, once these brute force solutions, they're really nice and powerful because once I tell you what I'm looking for, then all you have to do is list out all the possible things and check if that's what you're looking for, if one of those satisfies the definition of what you're looking for. So this was the definition of this arithmetic progression. So I just try all the I's, J's, and K's and see if any of them works. Okay. And now the running time here is very clearly n cubed because this loop executes n times. Each time it executes, this loop executes n times. And each time that executes, it executes n times. So in here, this inner code executes n cubed times. In fact, it's exactly n cubed times. So this runs in O of n cubed time. Now, can we make it faster? Can you think of any way to make this faster using any of the tricks that we've seen? Yep. We have to be careful because we really want to try different things where, I is 5 and j is 1 because, I mean, it could be that, a at 5 is 21 and a at 1 is 26 and a at, I don't know, 0 is 31. So we really need to try all the different orderings even of these things. So there's not even any shortcuts there we can take. Yep. Yeah. So the point is, once I know, if I have some candidates, AI and AJ, for example, here AI is 21, AJ is 26, then if I want to know if that's going to make an arithmetic progression, I know the third term in that progression. It's, well, the difference between these two is 5, so the next one is also going to be 5 greater than that. And so that's just asking me, once I fix AI and AJ, it's just asking me if some specific number is in my set. And checking if something is in the set is something we can use a set for. So we can speed this up to n squared by saying, creating a set out of our input. In this loop, we'll only want to check if AI is less than AJ. So that means it's a potential arithmetic progression. And we can finish it. And the way we finish it is by checking T, which should be equal to AI plus 2 times the difference between AJ and AI, right? So here we would set T is equal to 21 plus 2 times 5. And if T is in the set S, then we can return true. So we found an arithmetic progression. And that progression is AI, AJ, and T, where T is somewhere in the array, but I don't know exactly where yet because of this. If I wanted to know where it was, I would have to use a dictionary instead of a set, but this is good enough. And then otherwise we can return false at the end of this. So now what happens is we have a for loop that executes n times. Inside of that is another for loop that executes n times. But inside of that is all constant time operations. So this one actually gets sped up to O of n squared, down from O of n cubed. Okay, and we'll leave it at there for today.
I have a question for you.
Mm-hmm.
I didn't see the I didn't see Friday's lecture posted on CUlearn.